Counting. We're going to talk about divider problems and the pigeonhole principle. I have a couple of announcements here at the beginning. The first one is that we are going to move the test to next Thursday. So currently is now scheduled for Tuesday. We're going to move it to Thursday so we have more time to talk about counting in class. So it's going to be on Thursday next week. Also, that means it's going to give us enough time to have review sessions, and I'll go ahead and post when those are going to be. So they're going to be on Tuesday and Wednesday. Is that moved? Maybe we already had it scheduled for Thursday. Okay, good. Well, I was freaking out. Somebody told me it was Tuesday. So we're doing it on Thursday? Okay, so it's on Thursday. Our review, you're right, it's test 3. Review sessions are going to be on Tuesday and Wednesday nights. Tuesday is going to be 7 to 8:30, and Wednesday is going to be 5 to 6:30. And they're both going to be in this building, the other side, room 3211, which was the room you guys went to for the Test 1 study sessions. And your TAs will be holding those, and they will take food bribes. They have let me know that they like pizza and anything else you'd like to bring. What do they get you? They'll probably stay there longer. That's pretty much what it gets you. It doesn't change the grading at all unless you're feeding them while they're grading. It's pretty much how grad students work. Okay, so now while we're speaking about food, and I'm not going to give you any. You guys remember the story from last time. I'm not going to give you any food. I know you had the donut problem, but before we get to the donut problem, I know you're so excited to tell us your solution. How many people feel like they got the solution to the unique representation of donuts? Okay, so a few people. But first, we're going to talk about Char Grill. Okay, how many people have been to Char Grill? Downtown Raleigh? Like a third of you? This is so wrong. You need to go to Char Grill. It is a Raleigh institution. It's on Hillsborough Street, and it's like a drive up, and you put your order in at the window, and then they give you hamburgers and fries that you sit at a picnic table there and eat, or you can sit in your car, either one. And they're totally delicious, and you should go there. And they do not pay me, but I used to live like a block from there. So anyway, how do they take orders for food? Someone who's been there. Yeah, you have a ticket. And the ticket has places for what you want to order. So it's not like, you don't get a menu and you say what you want. You just write it on there and you slide it in the window. Okay? And it already has a form on it. And on the form, you mark stuff on there. And I'm not going to replicate the form. First of all, it's been years since I've been there. But I'm just going to put a few things on there. And you put, like, how many burgers. And then for each burger, you put, like, what toppings you want on there. But I'm just going to put a few things on here. And you put the number of each of these things. And you put X's for different things you want. I think they might do shakes. And you can put chocolate and vanilla, that sort of thing. So you can fill out this form and order your stuff. And you slide it into the window. Now, this form is like no one in the Char Grill has talked to you. They just take the ticket and they just make the food. Okay? The cool thing about this form is it uniquely determines what you're going to get. So I don't have different orderings that I tell people what I'm ordering at the restaurant. So when you go to some restaurants, you like McDonald's or something, you just go up to the counter and you tell them what you want, and they're like, or let's do the drive-through thing because it's the most terrible, especially if you have a husband whose accent is not straight English. So you order something and they're like, would you like 17 chicken tenders? And you're like, no, number one combo. So you tell things in different orders, right? And they're not even sure what they're listening for because there's so many things on the menu. But if you actually make the form, so like basically if there's a mark in this vicinity, you don't even need to be able to read the form, right? You get used to where everything is. You can like scan it and be like, oh, I'm making this many burgers, this many fries, this many this. So what this form does is it makes a standard format for people to make requests for stuff. And that's what we were talking about at the end of last class, is how do we make a standard format that we can actually describe different boxes of donuts that have the same number of donuts. Like we have 12 donuts in a dozen, and we were going to choose from 6 kinds, right? So this is an example of a standard kind of form where I could actually put ones for all of the different, like for the number of burgers I want, like hash marks for them. We'll say I have 3. So normally you wouldn't use hash marks, but I'm going to use them because we like binary in here. So we're going to put ones for things we want. But instead of putting zeros for things we don't want, we're going to put zeros for the lines where we're drawing stuff. So wherever I have a line here, I'm going to put a 0. Okay, and these are not circles to fill out. They're just zeros. So then, after I fill out a form, I can describe an order just by putting a string. I don't know how long it's going to be because it depends on how many ones people put in there. Okay? But the string for this order is going to be 111 0000. Because before I get to the line for the burgers, I got 3 hash marks. Okay? Let's make another one. So the string for this one's going to be 111 011 000. So that tells me 3 burgers, 2 fries, and nothing of anything else. Let's say I order a vanilla shake. Now the string is going to be 111 0 111 0. I didn't do anything for chocolate. Okay? And I don't actually need a 0 for this vanilla. So let's get rid of that one. So all of these have 3 burgers. These last 2 have 2 fries. And the last one also has a vanilla shake. How does that string change if I want 2 vanilla shakes? Add another 1 on the end. How about if I want to add some more fries? Add another 1 in here. So this is a unique way to represent all the different ways of getting anything from this menu. So every string is, I get 1s until I'm done getting all the burgers. Then I have a 0. And then I get 1s for however many fries. And then I get a 0. And then I get 1s for however many chocolate shakes. I don't like chocolate shakes. That's why there's none on here. I don't like vanilla ones either, but strawberry is better. Then I don't get any, then I get a 0 for ending the chocolate. And then after that, whatever comes after that is how many vanilla shakes I want. So a ticket is a way of making a standard notation for people to do an order, and you take out all the communication overhead that you have to do. We don't care about the communication overhead as much as we care about, now we have a binary string that represents the different orders. So if we're going to do that, we could do the same thing for donut orders, right? So for our 6 kinds, we could make a form. So before I talk about my solution, does anybody want to present their donut representation solution? Okay, so some people raise their hands, but they don't want to tell us about them. Okay, so since you don't want to tell us, I'd like you to come up with a solution for the 6 kinds of donuts problems on your own. I'll give you a couple of minutes. So try to use the same representation we kind of came up with, a ticket that we came up with from Char Grill, to figure out how you would make a binary string that represents the different ways I can have a dozen donuts. So that means I'm going to have how many hash marks? How many? 12. I'm going to have 12 ones. How many zeros will I have? I'll have 5 because I don't actually have to have 6. You could have 6, but if you did, you'll have extra stuff you don't need. So you need 5. What was your question? We're going to do a dozen. So we're getting a dozen in a box. And what I want you to do is write out a couple of example boxes and tell me what's in them based on your own representation. Okay, so all of our representations for a dozen donuts have 17 characters. They have 12 ones for where we're putting the donuts, and they have 5 zeros to divide the kinds of donuts. So you could imagine that you could even make your donut boxes so they had slidable like paper dividers in them, right? And you could just slide them and then not have your donuts touching each other. That would be awesome. In those long donut containers where they're vertical, the donuts are vertical. I know that would mess up your sprinkle donuts. It's all right. But you also do this like when you have like a drawer of pencils, right? You can put some, or your silverware, you put some dividers in it, but maybe they can move according to how much stuff you have in each bin. But the dividers tell you when there's the difference between two different kinds of things. And then all the things go in the bins because I can't tell those things apart, right? All the donuts should be the same, of the same kind, right? All of the chocolate should be the same. All the plains should be the same. So I don't care which one of these ones is in here. I can't tell them apart. So the reason why we're doing food problems for this one is food is the biggest example that we have where we believe, or where it's pretty standard that we could get like a whole bunch of the same thing, like M&Ms, right? They're all the same. You know, some people eat different colors, and that's how they distinguish the M&Ms is by the colors. Some people don't care, and so then they wouldn't count, you know, that it was a different handful of M&Ms according to which colors they were. Some people don't like some colors, right? So this is our representation. So we have 17 characters. Now, remember that I told you last time when we count things, the important thing is not the answer. The important thing is making sure we formulate the problem. So this is what we have done. We have formulated with a form a way of figuring out how to take orders for donuts in a representation that's totally unique for every different way of ordering the donuts. So I might get the order in different orders, but it's going to be on the form the same way. So I could even feed this to a computer, and it could just, you know, actually spill out all of the donuts we needed into a box. Because it would always be in the same order. Always get the plain first, then get the chocolates, then get the raspberries, then get the blueberries, then get lemons, then get strawberry sprinkles. So we've actually transformed it into a problem a computer can do. And we've transformed it into a problem that's easy to do. Now that I have 17 spaces for either dividers or donuts, all I have to do is choose where the zeros go. Right? Or the ones. It doesn't matter which one I do. As long as I choose where they go. So out of those 17 things, I'm going to choose the places for the 5 dividers, or I'm going to choose the places for the 12 ones, because whichever one I choose, the other ones have to be the other bit. So if I choose where the zeros go, all the other numbers have to be ones. So I'm talking about numbering the positions, where this would be position number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So remember we talked about when we're making strings, we actually can order all the blanks and then toss them in a hat and then choose which ones we're going to put things in. That's what we're talking about transforming this problem into now. Since we know that the length is 17, we can now number all the blanks and then we can just choose without replacement where we're going to put the zeros or where we're going to put the ones. Once we do the choices, the string is fully specified. So this is the mapping for problems that are called, what I call divider problems, and they have a complex description. But let's before we get to that, let's see what the formulas for these are. I wonder why they're the same. It's because the formula for combinations has k and n minus k on the bottom, so the formula for C and k is the same as the formula for C n, choose n minus k. So these two numbers, since one of them is k and the other one's n minus k, these two combination formulas end up to be the same, and just because of the formula. And it also should make sense, because it doesn't matter which one I choose. If I only have two choices of what I'm going to put in a blank, if I decide where some of them are going to go, the other ones don't get to have a choice. Questions about this? So about how many different ways are there? 6,000. That's a lot of different ways to order a dozen donuts, right? So now you see if Dr. Barnes had a donut shop, there would be a form you had to fill out so that my tellers wouldn't have to stand there and take orders and wait for people to decide which kind they wanted. Just fill out a form and bring it up here. Okay? Would I have it automated? Absolutely. Why do anything that you can get a machine to do? No, actually, I'd probably hire people just because jobs are good for people too. If I had a machine already, I would certainly use it. Okay, so there's a lot of choices. The important thing there was our mapping to a way of drawing out different boxes of donuts that have the same number of donuts in them but can have different kinds. So what you should do when you're working a counting problem is you should not write down a formula. You should start drawing a picture and writing out different things and then seeing if you have a representation that actually will count different things differently and count the same things the same way. So let's make this more clear. So for other boxes of donuts, what if I had 6 plain? So let's use our same representation, and 6 chocolate. So what is the string I would get for that? We started with plain, then chocolate was in the next one. So we do 1, 2, 3, 4, 5, 6. Put our divider between the plain and the chocolate. 1, 2, 3, 4, 5, 6. And then zeros for the other categories because we don't have any other ones. 1, 2, 3, 4, 5. So that is a string for 6 plain, 6 chocolate. Everybody who gets 6 plain, 6 chocolate gets it that way. Even if the person delivering the donuts takes a plain, takes a chocolate, takes a plain, takes a chocolate until they fill the bin. It doesn't matter. Yes? When I create my donut shop, I create how many kinds of donuts I'm going to have. So that's usually specified in the problem, like how many different kinds there are. The number of kinds actually determines the number of dividers. Let's say you want to make 6 columns on your page for all the different kinds of donuts. How many lines do you have to draw on the page to make it so you have 6 columns? You have to draw 5. So the number of dividers is always 1 less than the number of kinds. That's not really focused. Okay, and then how do we decide where the donuts go? We don't actually. Like, the person ordering the donuts decides. So I, as the person doing the counting and the person making the form, I decide which column has what kind of donut. And it doesn't matter where they are. So I just make the form, and then I just count all the different ways that people can fill out the form. So I put random labels on there. You can put whatever labels you want. Does that answer your question, Philip? Yeah, those are the remaining dividers. If I didn't have them there, I wouldn't know which 2 kinds these would be, because I could have leading zeros or I could have zeros on the end. So I have to have all the dividers there so I actually know, because the ones I get before the first divider are the first kind that I'm going to get out. And the ones after the first divider are the second kind. And the ones after the second divider are the third kind. So what you need to do when you do a counting problem is say, how do I draw a picture that represents one unique thing that I'm going to count? So this is one unique thing I'm going to count. I want all of the boxes that have 6 plain and 6 chocolate to have the same binary string. And this does that. Okay, so let's actually characterize these problems in a little bit more generality so we can kind of learn to recognize them. Now, you should be suspicious that when you see a problem that has kinds of food or kinds of anything, that it's probably a divider problem. Usually, though, these problems are hiding, and there's maybe not the word kinds in there. So let me give you an example. So the problem I wrote down is, how many ways are there for students to be distributed in the library if there are 100 students and 7 floors? So when you first look at this problem and you just only had the lecture that we did last time, you might be like, there's an and. That might be the product rule. So you have to ask yourself some other questions. Does order matter? And usually we're talking about order of something. Probably doesn't matter, right? In this problem? So the thing we were talking about before with the donuts is we can't tell them apart. So have you ever heard this word, distinguishable, in an annoying statistics and probability class, probably? So we're doing the mini statistics and probabilities portion of this class. Okay? So distinguishable and indistinguishable objects are probably the most annoying thing about counting. So if the items are not distinguishable, if they're in a certain category, you pretty much have a divider problem. So if the answer is no, not except, by what? What do I imply in the question here that I care about? Which floor they are on. So I'm kind of asking about the usage of the library, like what floors do people go to? That's implied by the question. It's not really explicit. And that's the big problem with counting problems, is almost all the time we have a not really explicit description of what we're trying to count. And so what we have to do is get it as explicit as possible. So, no, we can't tell the students apart except by what floor they are on. So all I really want to know, like you want to read between the lines of this question. This is a question that a librarian might ask for figuring out how to distribute resources. So if everybody's on the first floor and nobody's on the 7th floor, you might want to put some cool stuff on some of the other floors to get them to move around, because otherwise all your stuff's going to get worn out on one floor and nobody's going to use the other stuff. So you want to take your cool stuff and spread it around so people will go and not put so much wear and tear in one place. Or maybe you actually want them all on the first floor, because then your cleaning staff can just clean one floor. But you have to make decisions, and you're going to make them based on where people go. In a similar way, you're going to have to make decisions, like people make decisions all the time about where to put bus stops or how to run schedules, things like that. We have to count how many people are in places at certain times, and all we really care about, we don't care about who they are or where they're going. We just want to know what time you're going to be at the bus stop if I put it here. What time are you going to be at the bus stop if I put it there? Which bus stop are you going to go to? So we're basically going to categorize people by what floor they're on. And as soon as I can only tell people apart by some feature that they have, I'm talking about kinds. So now I can transform this into another problem where I can draw a picture of the library that looks a heck of a lot like a form. There's not 100 people in here, but basically I could draw a form like that and show you a distribution of people in the library at any time. And as long as the number of dots on any row is, different between two sheets, then they're two different representations, but I'm not caring about which student is where. I can't tell them apart except by what floor they're on. So now I've just transformed this into a divider problem. Every single representation is going to have ones where we have dots on here, and we'll have a 0 wherever we have the dividers. And then we'll have these floors. So two different representations, two different diagrams that have different numbers of dots on any two floors are going to be different representations. So I put an extra dot there, so and I took one off of there. So actually, put another dot there. So those are two different distributions of people at the library. So I've actually transformed this into, I can now represent it with a string. So I've got a form, but I can represent it with a string, which is ones for all the dots in one of the floors, and then zeros for the actual floors or the dividers in between. Okay, so this representation here, if I start with 1 on the left, it would be a 1, and then a 0 for this floor, and then another 1. So there's going to be zeros. So 1, 1, 1, 1, 1, 1, 1, 1. So 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1. So that's my first one. And my second one, we'll have zeros for all of the rows, ones for the peeps. And if we start at the bottom, we'll get 0, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1. Those are clearly different strings. They're representing different things. If I have the same number of ones and the same number of zeros, then I'm talking about distributing the people across the floors. So if I have 100 students and 7 floors, which things are the kinds? Which floor you were on? You have a question? You're right. Thank you for correcting that. So that is my correct representation there. So now, the kinds are the floors. So how many dividers do we have? We have 6 dividers. And if we make a string that has 6 dividers and 100 items, how many places do we need? We need 106, so we're going to take 106 slots, and we're going to choose where the 6 dividers go, or we're going to choose where the 100 students go. So these are my 2 answers that are equivalent. So we're numbering, everything in our string that we're going to have, and we're going to choose out of a hat either where the 6 dividers go or where the 100 students go. Questions? Okay, so the questions that are going to tell you you have a divider problem. If the answer is to does order matter is no. Are the items distinguishable? If the answer is no, not except by what kind or some category, then you know you're working with a divider problem. The other thing that you might ask yourself is there replacement? Again, another confusing problem because I'm not going to take a person out and replace them. So in the original problem that was specified, how many ways are there to distribute the students, there is a replacement because I can have more than one student, and I can't tell them apart. So this is intertwined with the distinguishable or indistinguishable problem. So if I ask you if there's replacement, I'm also asking you between distinguishable items. So yes, there is replacement because I can have lots of students that I can't distinguish from each other. So if I think about strings and replacement, if I'm saying, can I replace letters from the alphabet, if I can have 2 letters that are the same and I can't tell them apart, then yes, I have replacement. If that's possible, then I have replacement. So these 2 questions, if the answer is yes to whether there's replacement and whether the items are distinguishable, if it's no except by category, then you know you have a divider problem. So this is pretty much what a textbook would call a problem that is where order doesn't matter and you have replacement. And so there's not a formula for this kind of problem because you need to transform it into another kind of problem because it's too confusing to write it any other way. So you need to actually transform it into regular combinations without replacement. That's what this formula is for. So that formula is for combinations without replacement. So that's why I can throw all my numbers for positions in my string in a hat and then choose out where the dividers go. So that is a transformation from the original problem into a problem without replacement. And that's what we want to do because that's much easier to count. So these are combinations with replacement is what they're called. Okay, so let's do another counting problem. It's not necessarily going to be a divider problem. So how many ways are there to rearrange the letters in the word Mississippi? So again, what you should start doing is trying to figure out what does it look like when I do that. So I want to count all the ways of doing that. So for example, I could put all the I's first, and then put the S's, and then put the P's, and then put the M's. So that's an example of one of the things that I'm counting. That's one of the ways of rearranging the letters. Mississippi is one of them, right? So you should remember that the basics of counting is, in fact, what you really want to do is make a list of all of them and count them. But it's just like truth tables. Making lists is painful. So what we want to do is try to characterize the list so we don't have to make the list, we just know what the list looks like. And then once we know what the list looks like, we can count it. That's just one example. There's also the examples of Still leaving all the letters together, but changing the orders of them, right? And I'm just glomming them together. So this one's tricky. So how do we get started with this problem? What'd you say? Figure out the different kinds of letters. That's one idea. So then what would you do after that? Okay. So we'll figure out the kinds of letters and how many of each. And then what? Do the same thing we did in the previous one. Okay, so we could look at the number of letter options for the first place. So we have to know how many total items we have, right? So we can actually start drawing our places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we know that all of our strings are going to have 11 things in them. And I want to ask our standard questions first. Does order matter? Is there replacement? Kind of. Now you see why just memorizing some formulas and saying, if I have this and this, then I do this. It doesn't work. You need to draw a picture. You need to start characterizing what you're going to do. Now, I don't like this problem because there is replacement, right? Sometimes. So let's pretend there isn't any. So almost always when we want to solve a problem, we need to transform it into something that we know and like solving, right? So remember when we did our proof that square root of 3 was irrational? We're like, we don't like these square root things, and we don't like fractions? So we just get rid of them, right? So I don't like the fact that these letters are different. So I'm going to get rid of that fact. I'm going to number them. This is going to be I number 1. That's going to be I number 2. That's going to be I number 3 and 4. And again, I'm also going to label all of those. So now all the letters are distinct. Now that the letters are distinct, does order matter? Yes, it totally does because all the letters are different. So yay, I got rid of that. Is there a replacement? No, because I'm going to use every one of those letters exactly once. So I'm solving a partial problem to begin with. And then when I solve that, when I've actually done that, I'm going to fix it. So now that we have this, how many choices are there for blank number 1? 11. How many choices for blank number 2? 10. And we know the rest of the answer, right? Because each time I choose one, there's one less to choose, since they're all distinct and I'm not doing any replacement. So this is 11 factorial different ways. But we're not done because sometimes when I choose where to put an S, I've actually counted. So every time I choose the S's, there's how many orderings are there, of all the S's. So I have 4 S's. So each time I have my 4 S's distributed, I actually have counted every single way of rearranging S1, S2, S3, and S4. How many ways are there to rearrange S1 through S4? There's 4 factorial ways to arrange those. And how many ways are there to rearrange all the I's? 4 factorial. And how many ways to rearrange all the P's? Is that all the letters? Except for M, yeah. But M, there's only one way, right? Because we only have one M. So for every one of these 11 factorial, each one of them has 4 s's in them. And all those different 4 factorial ways of writing the s's are counted separately. So if I divide this by 4 factorial for those s's, then I've actually gotten rid of all the orderings of the s's. If I also divide by 4 factorial for all the reorderings of the i's and by the reorderings of the p's, then I've got my final answer. Because every single representation now has the s's. It's only counted once for the s's being in particular positions, and it's only counted once for the p's being in particular positions. So let me show you an example of what I mean. So let's just consider this string right here and all the different ways it would have been counted just with our 11 factorial method. Y'all were slow on catching that one. It's that time of the semester, huh? Yeah, there's squiggles. Okay. So let's look at these different ways. Now, 4 factorial is kind of a lot, right? So how much is 4 factorial? 24. So there's 24 different ways. So if I just look at the i's, I would have 24 different ways this string would have been counted, right? Because I would have our first canonical ordering one, and then the rearrangements of that. There's a whole bunch of them, right? And it's hard to make sure you're going to write them all down, because if you don't have an ordering that you're going to do, you'll just write them down and start looking for ones that are missing, and that's a pain. So I would have 24 different ways just to represent the same thing. The same thing here, 4 factorial ways to represent those orderings, 2 factorial ways to represent those, and just 1 factorial for that one. So in fact, we are dividing by 1 factorial as well, because that's how many m's there are, but 1 factorial is equal to 1. So we didn't put it there, but you can also put it there and it will not be wrong. So for all the different letters, so anytime I'm talking about a rearrangement, the top number is going to be a factorial, which is how many letters you've got. The bottom is going to divide out, for each category of letters that you have, it's going to divide out a factorial for that letter, however many it was. So this is just one string, and then whatever string I have, if I interspersed these i's and s's, that one will also have 4 factorial ways for the i's, and 4 factorial ways for the s's, and 2 factorial ways for the p's. And again, 1 factorial for the m's. So with counting, you really do have to make sure you draw a good picture or get rid of the answers to questions you don't like. Like if you don't like the fact that there's a replacement, figure out how to get rid of it and then fix it. That's what we're trying to do with proofs or with counting things. All right, let's do another problem. Now, this is one of the things that is really annoying to me. Is when different websites have different password requirements. It's really annoying because I have a few passwords I use and then I have to change them for these different websites. So annoying. Nobody else is annoyed by that? Yeah, okay, good. I heard some discussion on NPR the other day that passwords were over, and I was very happy about it. What'd you say? That's right. So we can have biosignatures to recognize ourselves, and we don't need passwords for devices that will actually be able to like take our fingerprint or take your pulse or other kinds of things. That can be hacked. Everything can be hacked. Passwords are the sort of simplest example of cryptography. So when we are actually encrypting something or hiding something like a password, all we're doing is just making it so that it has a whole bunch of possibilities, so it takes someone a really long time to figure out what it is. Because they would be guessing all the different ones, and then they would take a really long time to do it. Because factorials take a long time. And exponentials take a really long time. So all these numbers that we're calculating here, there's a lot of them. So if we have length 10, we have at least one letter, at least one number, at least one special character from this group of 4 characters, then we need to figure out how many passwords we have. Yes? Are we assuming the password is case sensitive? Which one would you like to solve? No. Are they usually case sensitive? Yes. If I don't specify on a problem, you should write down your assumption that makes the problem easier. And I had a clever suggestion up here. Let's assume that our keyboard only has one letter that works. We're not going to do that. We're going to say there's 26 letters. There's going to be 10 numbers. And we have 4 of these special characters. Okay, now, how do we start to solve this problem? The biggest challenge in a counting problem is usually when we can have different numbers of things that are the same, right? So order matters here, but we have replacement. So it's again, we might have replacement. We might not. So it's again an annoying problem. So we want to get rid of that. And one way to get rid of it is to decide exactly how many of each of these things we're going to have. And then solve that problem. And then do it for all the different ways of having exactly how many of each of those things. So let's assume that we have one letter, one number, and the rest are special characters. Now I'd like you to solve that problem. I'll give you a couple of minutes and just solve that one, and then we'll come back together. Okay, so let's talk about number 1 here. How many different ways are there to choose where the letter goes? 10. So I put my 10 numbers for positions in a hat, and then I choose out which one the letter goes in. And so remember that we always actually want to do an example, make something concrete. Try not to work in the abstract. So I'm just going to choose a place for my letter to go. And when I did that, there were combinations of 10 things taken one at a time, ways to do that, right? Because the order didn't matter which one I chose. I threw them in a hat. I'm going to pull one out, and I'm going to say the letter goes there. Then I'm going to choose where the number goes. How many choices do I have left? 9. I'm going to just pick a place for the number. So the way for doing that was 9 things. I'm going to choose one of them. Now the rest of those are going to be special characters, right? And how many special characters are there? There are 4, so in all the blanks, I can choose any one of 4 things, right? So I've got 4 choices in each of those. Now, these were just the ways to pick this position, but once I pick the position, there's ways of putting stuff in there, right? So how many ways are there to choose letters? 26. So there's 26 in there. And how many numbers? There's 10 in there. So I have to multiply all these together because remember that all of the letters in the password must be present. So all the numbers that went in those blanks, I'm going to multiply together. So it's going to be 4 raised to the what? 4 raised to the 8 times 10 times 26, and all of that's going to be multiplied by C10(1) and C9(1), all multiplied together, to give us this answer. So I separated the problem into phases. What I was going to do first, what I was going to do second, then, what was left. So the first thing I did was I chose where the letters went. That's an easy thing to do because I'm only looking at one thing at a time. I have 10 places. I'm going to choose exactly where exactly one letter goes. I'm not figuring out what the letter is yet. The next thing I did, I had 9 places left. I'm going to choose where the number goes. Easy problem. 9 places, choose one of them. By the way, what is C10(1)? It is 10. And what is C9(1)? It is 9. Okay, good. After I did that, I said, okay, everything else is a special character. There's 4 of those. So each of those I can figure out those 4. I knew that the letter place had 26 choices. I knew that the number place had 10 choices. That's how we do this problem. We have to separate it into phases of what we're doing. So this doesn't solve our whole problem, right? So we solved exactly a very small part of this problem. So what would be the next problem we would solve? What'd you say? What'd you say? The letter has already been, the places, so this particular place that I drew was one choice. But there were 10 other ways. So this already counts all the ways of placing the letters and all the ways of placing the numbers and the special characters. This is the answer for exactly one letter, exactly one number, and the rest special characters. So now I'm going to have to do exactly 2 numbers, or let's do 2 letters and 1 number, and then the rest special characters. Okay? Okay, so we're going to do 2 letters, 1 number, and the rest special characters. Now let's look at our formula for the prior problem. Our formula for the prior problem said, okay, from the 10 places I'm going to choose where to put the letters. And there are 2 of them, so I'm going to choose 2. Then I'm going to, from the remaining spots, I'm going to choose how many numbers I have. And then I'm going to tell how many ways there are to do the special characters. It's going to be 4 raised to the number of slots left, which is 7. And then it's going to be 10 raised to however many numbers I've got. There was 1. And then 26 raised to however many letters I have. So each one of the blanks has to have a number in it. So if you look up here, the powers add up to what? They add up to 10 because there are 10 blanks, and there has to be a number in every blank. So if it's a letter blank, it has 26. If it's a number blank, it has 10. And if it's a special character blank, it has 4. Now we need to do 1 letter, 2 numbers. I'm surprised I haven't heard any groaning yet. Okay, you're just being nice or something, yes? Okay, that's a good idea. So remember when we did truth tables, we had to write out all the possibilities. That's what we're doing. We're writing out all the possibilities of having at least 1 letter, at least 1 number, and the rest special characters, and at least 1 special character. So we had an idea at the front here. This is a pain in the butt, right? That doesn't mean you shouldn't do it. It means if you come up with a better idea, you should do that. But if you can't, this is what you have to do. Now, it's not that horrible, but it is a pain. So let's see what the other idea is. So we have an idea in the front. What was your name again? Nathan? Nathan had an idea. And he says, why don't we come up with all of the possibilities and then subtract off the things we don't want? So just like when we did the combinations and we chose the dividers where the dividers go, the other blanks had to have the items, or we could choose where the items go. So almost every counting problem has an opposite problem that might be easier to count. Okay, so we know that our password is length 10, and we have the total characters that we could have in any blank is 26 plus 10 plus 4, right? So any blank could have that many in it if I just make any password that uses that set of characters. So this is one blank, and I got 10 of them. So that's going to be 40, and there's going to be 10 of them, so I'm going to raise it to the 10th for the number of passwords of length 10 with this character set. Does everybody understand that? Okay, what kinds of things do we have to subtract off? So if we have all numbers, if we have all letters, all special characters, if we have letters and numbers only, right? And letters and special characters only. And if we have special characters and numbers only. Now this is a lot less than all the different ways of adding up the number of exact counts for each of those different things. So how many strings are there that are only numbers? 10 raised to the 10th, because each blank only now can have a number in it. So it has only 10 choices, and there's 10 of them. All letters is easy. 26 raised to the 10th. So there's 26 letters. 10 blanks. Multiply 26 together 10 times. Okay, all special characters, that's 4 choices raised to the 10th. So we're going to subtract each of those. And these are distinct from these. So there's no string that is all numbers and all letters at the same time. So I don't have to worry about the inclusion-exclusion principle that says that I have to add back the intersection, because none of these have intersections, right? That's a really important thing in counting, is make sure that when you're subtracting things or adding things that they don't have intersections, or if they do, you have to count them and add them back in or subtract them back out, depending on what you've been doing. Okay, now letters and numbers, that means I've got 26 letters and 10 numbers, so that means all of my ways of doing that is 36 raised to the 10. Letters and special characters is going to be 30 to the 10. And special characters and numbers only is going to be 14 raised to the 10. So I'm going to subtract all of these, and we'll have our answer. 40 raised to the 10th minus 10 to the 10th minus 26 to the 10th minus 4 to the 10th minus 36 to the 10th, 30 to the 10th, and 14 to the 10th. That's still really, really large, right? Really a lot of passwords. Did you get it on your calculator?
Yeah, it's like
6 quadrillion. I don't even know how many zeros that is. So I don't actually care if you write this number down on anything. So remember that when we solve counting problems, Dr. Barnes does not care what the actual number is. She only cares about the formula. Yes? Well, if we can have between 8 and 16 characters for a password, then we add up all the possible lengths. So that's why it gets even worse when people can have however long they want. So that's why there was a really good article about 2 years ago, maybe it was 3, that was on how to write a good password. And it basically suggested that you should just write yourself a long sentence that's really easy for you to remember, because it's much easier for people to remember words and sentences than it is for them to remember anything else. And it really starts to get hairy if a computer has to generate all possible permutations of letters for passwords to figure out your big, long password. So, I love cookies, and then sprinkle some special characters in there. That's already longer than most people's passwords, right? And it's easy to remember. So you could pick something you love, write a sentence about it in your own special way, and then it'd be hard for someone to figure out. So it's not so hard if everybody was only using passwords that had words in them, then they could start using dictionary combinations, but it still really would take a long time for the search. So the reason why I'm talking about how long it takes for a search is that the reason why we do counting is usually to figure out, do we have enough variability, right? So if I have a whole lot of people, I got to have a password, requirement that's going to allow me to have, people not to have overlapping passwords. That's why we don't have 2-letter passwords, right? It would be really quick and easy, as soon as you guess one, no, you can't have that one. No, you can't have that one. No, you can't have that one. Someone's already got that. How many different passwords can we have if we only have 2 letters? 26 squared. So as soon as that many people have them, they're gone. So if you have more than 26 squared people, and you also don't want password collisions, you don't want to tell people that they can't have a password, right? Because then they get the hint. That's actually information about your system. You don't want to give away information about your system. Because then people would know, oh, that password's already taken, so I can actually now start, actually just requesting I want this password. No, you can't have that one. And then you start knowing that there's people with those, so then you can start searching the username database. So to protect systems, that's why you don't give out information about that kind of stuff. Okay, the last thing I want to do is introduce what's known as the pigeonhole principle. Okay, the pigeonhole principle is a funny statement, and it says, if you have more pigeons than you have holes, and all the pigeons are going to the holes, then you can prove that there's at least 2 pigeons in 1 hole. So for this problem, for this principle, you need to imagine like a bunch of cubby holes where pigeons sleep. And if you have more pigeons than you have holes, they will start cramming in them. That's what they do. They like to perch where they live, and they go sit in the holes. And sometimes they'll cram together even when there's empty spaces. They don't make sense. They're not very smart. But they're allowed to go wherever they want. You don't have control over the pigeons. They can go wherever they want. You just give them some holes that they can go to. But you can guarantee if there are more pigeons in the holes, at least one of the holes has got a few pigeons crammed in there. Makes sense, right? So what we usually do when we're talking about the pigeonhole principle is we usually think about the most even possible distribution of pigeons. Let's say I could make them do stuff. So I make them go, when you go parking for a festival or something, they make you go to the next available spot, and they've got people waving you. Go this way. No, don't park over there. You go right here. You have to go to the next available spot. So let's assume we do that with our pigeons. When they come in, you go to the next available spot, and I make you fill it up. So this is the most even distribution we can imagine. When I fill up all the holes, I'm going to wrap around again and start at the beginning and start making them pair up until I fill them all up again. And then if I get even more than twice the number of holes, I start over again. So when we start thinking about how many pigeons we can guarantee are in a hole, we actually think about the case where I'm maximally separating the pigeons as much as possible. What that means is evenly distributing them between the holes. That doesn't mean that that's what we're guaranteeing. We're just saying if they were all spread out as much as possible, we still could guarantee a certain number in each hole. So there's a more general principle, is that if you have N pigeons and we have K holes, then we can guarantee that we have the ceiling of N over K pigeons in one hole. So this is the more general, is if you have N pigeons and K holes, then you can guarantee that there's the ceiling of N over K pigeons in one hole. And this seems really simple, but then you can start to ask some really complicated questions. So, let's ask a question. So you're having a party, and you're going to have N people at the party. And they bring 8 cars. If we can guarantee that there exists a car that has at least 4 people in it, what's the minimum number of people at the party? So again, go back to that most dispersed distribution. If I can guarantee that there are at least 4 people in the car, that's going to occur. Think about my holes. The cars are the holes. I'm cramming people in holes evenly. So I'm putting 1 in each car. So I fill up 8 of them, and then I put 1 in each car. So I have 16. And then there's 2 people in each car. And then I have 16 plus 8 is 24. Then I have 3 people in each car. And then after I fill up that many, 3 people in each car, that's 24. After I get to 25, one of the cars has 4 people in it, right? So if I have the most even distribution, if I have 25 people, then I can guarantee that there is a car that has at least 4 people in it. There might be more than one, but the most even distribution, if people try to get as far apart from each other as possible, we can do that with 25 people. So at least one car had to have 4 people in it. So that's it for today. We'll talk about this some more next time.